That's not very loud. There we go. So today we're going to do more equations. Yesterday we did logarithmic equations. Today we're going to do exponential equations. So by the end of today, you will be able to do the first part of the homework assignment. So you'll be able to finish part 1. I have a worksheet almost ready for tomorrow. There's still quite a bit that needs to be done, but I have help here with my son. So I'm hoping between this class and my next class, I'll be able to finish that worksheet and send it out. But there will be a worksheet being sent out. You'll definitely want to print it if you have access to a printer, purely because it's going to be, where is it? Right now it's 7 pages long, I guess, and it's going to be longer, and it'll save you a lot of writing. And I'll try to get it out before it's late tonight. My goal is to get it out before my next class. Fingers crossed. So look out for that today. Hopefully not tonight. Cool. All right. So today we're going to talk about exponential equations. I already said that, but I'm going to say it one more time. Exponential equations. All right, so kind of like we did yesterday, I want to go over some important facts about exponential equations. So some important things you need to know before solving exponential equations. I'll talk about the procedure, and then we'll do a bunch of different problem types so that we are prepared for the homework. All right. So the first fact, and I think this is probably the most exciting fact, it's the distinct difference between logarithmic equations and exponential equations. With logarithmic equations, we had to worry about domain restrictions. So we had to worry about, like, does our answer fit in the domain of the original logarithm? Exponential equations, you don't have to worry about domain restrictions. So if you get an answer in an exponential equation, as long as you did everything right, that is your answer. You don't have to check your answer to see if it makes the inside of the logarithm negative or anything. That doesn't happen with exponentials. So let me write. Now, you're always welcome, of course, to check your answers in the original equation. It's a great thing to do. You can find out if your answer is right or wrong, but you don't have to as an absolutely necessary step of the procedure. So that's an exciting fact about exponential equations. Next fact, if m is equal to n, then log base b of m is equal to log base b of n. And you may say, that's what we had yesterday. We already had that rule, which you could say that because it's very similar. But the rule that we had yesterday was that if the logarithms were equal, then the insides were equal. So this is like the synonymous statement for exponential equations, but it's the other direction. So it's if the values are equal, then you can, as we say, take the log of both sides. So if you have something, if you have an equation, you can take the log of both sides of the equation. So you can take the log, you can take the ln, you can take the log base b, you can do whichever base of a logarithm you want to both sides. Just like you can multiply both sides by any number. You can subtract any number from both sides. You can apply a logarithm to both sides. Let's use purple. Three. These are two rules you already know because we talked about them when we talked about the properties of logarithms, but I'm going to bring them back quickly so that we remember them. So first things first, if you have log base b of b raised to the x, the log base b of b cancels and you just get x. All right. So with logarithms, with just like log base 10, the way that that would look, if you have log of 10 raised to the x, this is just x. With ln, since the base is e, if you have ln of e to the x, this is equal to x. And then if I just choose a random base for showing you how it looks, let's say log base 4 of 4 raised to the x, that would be x. Another one that we have, and this one follows directly from this rule, if imagine if x was 1, so you have b to the first power there, then you would have log base b of b is equal to 1. And for the base 10 logarithm, that means that log of 10 is 1. And then for base e, ln of e is 1. And then we just choose a random base here. Let's choose 8. Log base 8 of 8 is 1. Finally, last thing we need. If b raised to the m is equal to b raised to the n, then m is equal to n. Right, so if you have both, sort of like with the logarithms, where it's like if you had log of something equals log of something, that you could set the somethings equal to each other, this is that equivalent statement, but in the exponential form. Now, I want to give reasoning for this because I think the reasoning fits in very well with the tools we're going to be using today for solving equations anyway. But imagine you have b to the m equals b to the n. If I wanted to prove that if b to the m equals b to the n, then m has to be n, I could start with this equation, and then I got this rule that said I can take the log of both sides. So I'm going to take the log of both sides of this equation. So I'm going to take the log base b of both sides. Okay, taking the log of both sides. And that cancels, right, the log base b part. Using this rule right up here, log base b of b to the x is x, so log base b of b to the m is m. So then you get m is equal to n. Super cool, super fun. And if that's something that tickles your brain in the right way, if you're looking at that and you're like, oh, that's kind of cool, like how the math works there, maybe math majorism is for you, because as you get further in math, you do more stuff like this, where you're proving that things work. You're proving that statements are true. the further you get in math, the less numbers you see is a true statement. All right. Those are my fun facts. Let's move on to the procedure. How about fractions? How many of those later on? Do they ever go away? Yes, you still deal with fractions. You deal with fractions, but you're not dealing with numbers. So you'll deal with a lot of variables, but you won't see a lot of numbers. I wonder if I know this is like complete sidetrack right now, but I'm wondering. I go to this one. School. I was wondering if I had my like thesis handy and I could show you guys like how my thesis ended up looking. This was pretty cool. It was pretty awesome. But I don't see it easily. But short answer is no, fractions don't go away. It's just the fractions no longer have numbers anymore. They just have variables. I think it's way better. I think that the math you do as you go further on in math is a lot more satisfying. But it's a lot less computing numbers, and it's a lot more, like I said, like proving that things are true. Basically constructing math for yourself, constructing the basis of math for yourself. It's pretty neat. It's pretty great. All right. So the procedure for solving exponential equations. You need to simplify it to one of three forms. Now, technically, there's one procedure that could work for all of these. However, I'm going to give you different procedures for each of the cases to give you the easiest procedure for solving these equations. So first, you need to simplify to get to one of the following forms. Let me write. Simplify to get your equation to one of the following forms. So we have form A. This is going to be B raised to some power is equal to B raised B raised to some power, i.e. these guys have a common base. And if you can get a common base, if you can simplify your equation so that each side has a common base, then we can use this rule right here that says if we have b to the m equals b to the n, then m is equal to n. So we can set these exponents equal to one another. Yeah, let me use this little. That's form A. Form B. Oops. Shut this window real quick. So form B, maybe you can't make both sides have the same base, in which case you have B raised to something equals C raised to something else. In this case here, you're able to take any log. You could take log of both sides. It could be any base. The easiest thing to do is to use base E so that you can use ln, because ln is faster to write. When you have to choose which base to use, and it doesn't matter, the base doesn't matter, ln is always going to be the fastest because it's 2 pen strokes as opposed to 3 pen strokes to write log. So you would take the ln of both sides, and it would bring down the exponents, and you'd go from there. So this is what you do when you have no common base. Finally, we have form C. This is where you get B raised to the something just equals a number. So like there's no exponent on the other side. In this case here, you're going to apply to both sides the logarithm that has base B. Right? You're going to apply log base B, and then use the fact that log base B of B to the x is equal to x. But in our case, since we have B raised to the whatever, this is just equal to the whatever. So those are the 3 different forms. We're going to get examples of each of those. Don't you worry. If you're feeling a little overwhelmed by that, we will be doing examples. The one I kind of want to talk about is this form A one, real quickly, because sometimes you're going to be doing you end up having a form A without like thinking that it's a form A. So I want to talk about common base families. i.e. numbers that have the same base. Numbers that are all powers of the same number. So 8 and 4 are both powers of 2, for example. So with 2, we have 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. I'm just going to kind of write down up to the most common ones that you see. 2 to the 4th is 16, and 2 to the 5th is 32. That's the 2 family. For the 3s, 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. And let's see, 3 to the fourth power is 81. 3 to the fifth power is 243. Don't worry, I'm not going to do, it's not going to be this extensive for each of them. Really, you end up seeing 2 3s. You see the 2 family, the 3 family, the 4 family, and the 5 family a lot. 4 raised to the first power is 4. 4 squared is 16. 4 cubed is 64. And 4 to the fourth power is 256. 5 to the first power is 5. 5 squared is 25. 5 cubed is 125. So each of these are common base families. So 2, 4, 8, 16, 32, they are all in the same common base family. 3, 9, 27, 81, 43, they're in the same common base family. 4, 16, 64, 256, all in the same common base family. They're all powers, these are all powers of 4, all powers of 3, all powers of 2. And this is going to come in handy. This is going to come in handy. Eight raised to the 3x minus 1 is equal to 32 raised to the x. So you may look at a problem like this and think, okay, it's not form A because they don't have the same base. So it must be form B because they both have exponents. So it has to be form B that we're looking at here. And you technically could treat it like it's a form B. However, 8 and 32 are in the same common base family. They're both powers of 2. So these can both be rewritten as powers of 2, and we can make it into form A. So 8 is the same thing as 2 cubed. 8 is the same thing as 2 cubed. 32 is the same thing as 2 raised to the fifth power. So what I'm going to do is replace 8 with 2 cubed and 32 with 2 raised to the fifth. So I have 2 cubed instead of 8, 2 cubed raised to the 3x minus 1. And then instead of 32, I have 2 to the fifth raised to the x power. So I took this equation here, and I replaced the 8 with 2 cubed, and I replaced the 32 with 2 to the fifth, and then left the exponents alone. An exponent rule that you need to remember here is that if you have x to the a raised to the b, this is x raised to the a times b. So you multiply those exponents in that case. So here, 3 is going to get multiplied with 3x, and it's going to get multiplied with negative 1. So we have 2 raised to the 9x minus 3. 2 raised to the 9x minus 3. I'm going to make my 2 a little bigger. is equal to 5 times x is 5x. So 2 raised to the 5x. And now it's in Form A. Both sides have the same common base. So if I look back up here, let's see if I can group. Oops. I just wanted to bring this along with me, to have this along for the ride. Ungroup, erase all the extra stuff that got duplicated, except for oops. Regroup. Cool. There we go. So with Form A, we have the bases are the same, so we can set those exponents equal to one another. So this exponent here because both bases are 2, we can set equal to 5x. So we get 9x minus 3 is equal to 5x. I can subtract 9x on both sides, and I get negative 3 is equal to 5 minus 9 is negative 4. Dividing both sides by negative 4, I get 3/4 is equal to x. So once again, my first step here was simply recognizing that 8 and 32, oops, not my pointer, that 8 and 32 were in the same number family, the same common base family, right? 8 and 32 are in the same common base family, which means that I could rewrite them with the same base. Once the base was the same, I could set this exponents equal to each other, and then this is just solving a linear equation. Can I answer any questions about that so far? Accidentally did it on the homework, but wasn't fully understanding how I was doing. Well, hopefully then this will help. Hopefully it'll help to see it, to see a few more examples. You're like, yes, that's how it was supposed to be done. Yeah, there's the exponential problems. I think you definitely need to see a few examples before you can feel confident in it. I don't think it's something that most students would look at. I don't think most students would look at this equation and know where to go without having some type of information given beforehand. I would be very, very impressed if I gave a 126 student this problem and without doing any research or having any lecture, if they knew how to solve it, I'd be so impressed. I think it's definitely necessary to have those examples presented to you first. So let's see. Let me go ahead and okay. All right. So we have 5 times 2 raised to 3x plus 1 plus 1 is equal to 16. Before you can make any judgments, we need to get this guy into the form of one of these, right? we need to isolate the term that has the exponent on it. So if I'm looking at this, and I see that only one term has an exponent on it, it could still turn out to be a form A, but we want to at least put it into form C. So we only have one thing with an exponent on it, so we want to get the exponent alone and the number on one side. This is going to happen very similarly to the way that you would kind of solve a linear equation to get 5 times 2 to the 3x plus 1. Not 5 times, to get the 2 to the raised to the 3x plus 1 by itself. Now, really, really important, all right? Caution, caution, caution. You are going to feel very tempted, very, very tempted. Maybe I'll just make it in red. And you do have one of these types of problems on your homework. You're going to be tempted to do 5 times 2 is 10. Don't do that. You cannot do that. And here's the reason why. Here's why you can't multiply the 5 and the 2 together. Because 2 has an exponent attached to it and 5 doesn't. Right? We can't multiply these together because this guy has this many copies of him. And that would be multiplying every single copy of 2 by 5. But we're only multiplying everything. We're multiplying all the multiplied copies of 2 by 5. So you can't multiply these together. If he has an exponent, then we can't multiply these together at all. The way that you're going to treat this to get the 2 raised to the 3x plus 1 by itself, it's as if you have 5 times something, all right, plus 1 is equal to 16. If that 2 raised to the 3x plus 1 is making you uncomfortable, treat it as if it were just a box. How would you get the box by itself? You would start by, I promised myself I wouldn't write out the math here, subtracting 1 on both sides. So you would have 5 times whatever. Is equal to 15, subtracting 1 on both sides. You would divide both sides by 3. Not by 3, by 5, you get 3. I will write down this math quickly. Oh my gosh. That leaves you with just whatever equal to 3. So in doing this math to get 2 raised to the 3x plus 1 by itself, it's like you're putting, all right, I know I just shrunk them down immensely, but it's like you're putting 2 raised to the 3x plus 1 into that box. It's not going to work to actually try to put it in there. And that's how you're going to get 2 raised to the 3x plus 1 completely by itself. Let's see how that looks. So again, I'm subtracting 1 on both sides to get rid of that 1. That leaves me with 5 times 2 raised to the 3x plus 1 equal to 15, because we subtracted 1 on both sides. Maybe I will write it just for clarity. Then I'm dividing both sides by 5 to get rid of that 5, so that you have 2 raised to the 3x plus 1 is equal to 3. Any questions on getting to this form? We're not done yet. We haven't solved it yet, but any questions on getting here? Okay, excellent, excellent. So at this point in time, it's not going to be Form B, right? It's not going to be Form B because Form B has exponents on both sides and no common base. It could be Form A if 2 and 3 were in the same common base family, but they're not. Now, again, I am highlighting these, hoping that you are highlighting them too in your notes, so that when you go to look at your notes while you're doing the homework, that you, if you're like, oh, this is a Form B problem, that you can just scroll and look for the blue highlighting to see where the Form B problems are. And this is actually just going to have to flat out go on the next page. There's just not going to be room. All right. So this is Form B. That means we need to take the logarithm of both sides, the logarithm base 2. So if you'll notice, if I bring this guy down here, come here, move. With Form B, you're supposed to apply I meant Form C. Send help. Please send help. I know I've been complaining about sleep all semester, but the past 2 nights have been incredibly bad for sleep. So my brain is sorry, Zach. I wish I had something to say. So you're doing Form C, which means you're going to apply log base, whatever base you have, to both sides. So this one will apply log base 2 to both sides. So applying log base 2 to both sides, you get log base 2 of 2 raised to the 3x plus 1 is equal to log base 2 of 3. I should have given that one a little more room. Maybe write that a little clearer. 3x plus 1. Okay. You're doing this because log base 2 of 2 raised to the 3x plus 1, those all cancel out. We have a rule that if you have log base 2 of 2 raised to whatever, that this is just equal to the whatever. So the log base 2 of 2 part cancels. You're left with 3x plus 1 is equal to log base 2 of 3 To solve for x, I am subtracting 1 on each side. Maybe I will write this math out. Then you get 3x is equal to log base 2 of 3 minus 1. Divide both sides by 3. Your final answer, x is equal to log base 2 of 3 minus 1 all over 3. Now, this could have been done another way, but this honestly makes it a little easier. If you have a case where there's only an exponent on one side, so you're choosing basically between is it form B or is it form C? If there's exponent only on one side, you're in form C. It's easier to take the log base 2 on both sides because it completely wipes out the 2 altogether. If you instead treated it like it was form B and took the ln of both sides, you could still bring the exponent down, but there's going to be a little bit more distributing, a little bit more work to do. These problems can get the tiniest bit messy. All right, you can get the tiniest bit messy. And let me kind of show you. 11 raised to the 6x plus 5 equals 2 raised to the 2x. This is just flat out in form B. The bases are not the same, and they're not in the same family at all, and there's exponents on both sides. With form B problems, we apply ln to both sides and we bring down the exponents, and then we solve for x. Delete that. So we're applying ln on both sides. We have 11 raised to the 6x plus 5 equal to ln of 2 raised to the 2x. Now, I know that I'm not sitting there looking at your guys' work, but I am going to tell you a quick story about notation to hopefully deter some of you from doing this notation that you might be tempted to do because you're in the privacy of your own home and you don't think I'm not looking at that work, so you think it's okay. It is tempting. Here's the thing. It is tempting when you take the ln of both sides to want to do this. All right, that is tempting to write it like that. Now, let me tell you, when I was in college, there was and I was taking calculus, there were problems where we had to take the ln of both sides, and I would write it like that. And I was at the school's tutoring center, and one of the tutors was like, "You can't do that." I'm like, "No, I know what I mean. I know what I'm writing. it's fine. It's just my own notation. He's like, you can't write it like that. You just cannot. And now looking back, I like cringe so hard that I wrote it like that. But ln doesn't ever go, you can't do it like this. ln is not multiplication. ln is an operation. It would be like trying to write square root of 4 as 4 square root. That's what it would be like. And being like, I know what I mean when I write this. It means square root of 4, but that's not, okay, that's cool that you know what it means, but it's not the way that it works. So just fun fact, when you take ln on both sides, the ln does need to come first. That's just how the notation works. So when we've taken the ln of both sides, we're able to take down these exponents because that's what logarithms allow us to do. They allow us to take down exponents. So this exponent comes down in front. We get, in parentheses, 6x plus 5 times ln of 11. Is equal to 2x times ln of 2. So those exponents came down in front. The rest of this is very procedural, and it's a lot like when we did inverses. We did these inverse problems. Oh man, what day did we do inverses? Man, I wish I could go back and find that, but I don't even have a schedule handy. When we did inverses, we did those problems where like you had to multiply both sides by the denominator, and then you distribute it, and then you had to like recollect the x's. If you don't remember what I'm talking about, you're going to remember as soon as we start doing this because this procedure is going to look very similar. To get x by itself, we're going to start by distributing this ln to both of these terms. So we get 6x ln 11 plus 5 ln 11. So the ln 11 got distributed to both terms. That's what happened on this step. We distributed. For the next step, maybe I'll just write that up here. Or maybe I won't write it at all. For the next step, you need to collect all the x terms on one side. So all terms with x need to be on one side, anything without an x on the other. So this guy has an x, so he's going to stay. This one needs to move over to the other side. So I'll be subtracting it off both sides. This guy doesn't have an x in it, so he needs to move to the right side. So I have 6x ln 11. I'm moving this guy over to the left side, so he'd be subtracted on both sides. He's going to be subtracted minus 2x ln 2. And then this guy moves to the right side, so I'd be subtracting him on both sides. So I have minus 5 ln 11. So if it helps here, I'm not sure if it does. No, I'm not sure that color coding actually helps there. Does it make sense how I move these guys around? So this guy, he got subtracted on both sides. This one also subtracted on both sides. I see at least one person says yes. Any questions from anyone else so far up to this point? I see how, but why? Excellent question, Brooke. I love it. Because now that all the x terms are on one side, we can pull x out. We can factor x out. Excellent question. So if I factor that x out, I have 6 ln 11 minus 2 ln 2 is equal to negative 5 ln 11. But then why not move the 6 ln 11 too? So he stays here. Yeah, exactly. It's the 6x. Yeah, he stays here because of the x. Because that way we can factor that x out of both of them. Because they both had that x right there. No problem. No problem. Then all that's left to get x by itself is dividing both sides by 6 ln 11 minus 2 ln 2. So you're dividing by this hunk right here. And that gives you x completely by yourself. So we have x is equal to negative 5 ln 11 over 6 ln 11 minus 2 ln 2. So I actually love these types of problems. I think these types of problems are really, really fun. They look really messy, and I think that's kind of what makes them fun, is because it makes the answer look super smart, super smart and complicated, but it's totally an achievable answer. You guys are capable, more than capable, of doing the math to get down to this answer, and look at how fancy your answer looks. Now, I will tell you, on my lab, they are also going to have you give an approximation. So it'll ask you for the exact answer, which would be this, and then an approximation where you would type this into your calculator. Right? So the first part will be the exact answer. The second part will be the approximation. If you have your calculator on you and you want to practice the approximation to see, to make sure you're able to enter this in your calculator correctly, let me enter it into mine and tell you what it approximates to. Negative 0. I don't know how many decimals they said. I'll go to 3. What if I don't have a calculator? I've tried using online calculators for the approximation, but none work. You will need a calculator. You will need a calculator. It technically is a required, it's technically a required resource for the class. It'll also be a lot easier to do on the calculator. Even using the online ones, you're gonna have to be so careful about your syntax that it's going to be really obnoxious trying to enter it onto the online ones. But this one here, if you're going to go into calculus at all, or trigonometry, which is the next class after this one, this calculator, the Casio FX991EX, it's the one I suggest in the syllabus. It is a calculator that costs less than $20, and it will do you so well. So I highly suggest it. Yeah, I mean, and to a point you probably can, but like if you're going to take more math classes, it's definitely worth it for your own sanity to own a calculator. You can still try, you can still try entering it online. Like I'm sure you could enter it on Wolfram Alpha and get the approximation. Like I said, you're just gonna have to be super careful about the syntax, because you're gonna have to put parentheses in all the right places. If you don't put the parentheses in the correct places, then it's not gonna read your answer correctly. It becomes a lot more complicated, unfortunately. My problem with MyLab rounding to the decimal points, it's picky. It changes how many decimal points it wants and when to round and when not to. Yeah, you have to read that the fine print every single time. With the fine print, you have to make sure, is it asking for an exact answer or is it asking for an approximation? If it is asking for an approximation, how many decimal points? Double check to make sure, because every problem is different. Wish I had wish I had something better to say than that, but that's about all I have to say on it. All right, which one of these did I want to do? That one works good. All right, 12 raised to the x minus 2 plus 7 is equal to 5. 12 raised to the x minus 2 plus 7 is equal to 5. We want to get it into one of our approved forms. Move you down. Get into one of our approved forms. I'm going to start by subtracting this 7 on both sides. So I have 12 raised to the x minus 2 is equal to negative 2. Okay. These do not have the same base. They're not in the same base family. We don't have exponents on both sides. So this is going to be form C. Which means we want to take the log base 12 on both sides. So I'm applying log base 12 on both sides here. 12 raised to the x minus 2. And now I'm going to stop for a second. I applied log base 12 on both sides. And this is something that you may not catch if you're just kind of beginning to work with logs, but something happening on that right-hand side is not going to sit well. What is going on here that's making me sit, pause, and make a big deal? What is going on? The negative. Yeah, you can't have a negative inside of log. It's inappropriate. You can't have a negative inside of log, so that like it's not a real number. This has no solution. No solution for that one. Like 2 things I want to do, and I'm trying to debate. Yeah. Okay. Any questions on that example? Okay. I want to now, which one did I want to go to? Bum, bum, bum. Okay. There's 2 things I want to do. I want to redo 2 of these problems using a different technique so you can kind of see the versatility in solving exponential equations. So with this first one here, 8 and 32 were both powers of 2. I put it into form A. We set the exponents equal. We got an answer, right? This isn't the only way to get this answer. And I want to talk about the other way. And I also want to talk about this guy down here, 2 raised to the 3x plus 1 equals 3. We applied log base 2 to both sides and got an answer, but that wasn't the only way to do the answer. So let me start with the 2 raised to the 3x plus 1 equals 3. And let's try doing this a different way. Before we applied log base 2, but I want to show you that if you applied ln, you could have got the same answer. It'll look very different. It'll look very different, but it will be the same answer and the correct answer. So applying ln this time, if we were to instead apply ln, so ln of 2 raised to the 3x plus 1 is equal to ln of 3. This exponent up here, we take the ln of both sides, which allows us to bring the exponents down. So I'm going to bring the exponent down in front. So I have 3x plus 1 times ln 2 is equal to ln 3. So this is the exponent that I brought down. I can do this just like I did in that the problem right before the no solution problem. I am going to distribute that ln. I get 3x ln 2 plus ln 2 is equal to ln 3. I want to get the ln to the x by itself. So there's only one term with an x in it. He'll stay there, and I'll move everything else to the other side. This is just kind of the theme of using ln's. So subtracting ln 2 on both sides, 3x ln 2 is equal to ln 3 minus ln 2. And then I can divide both sides by 3 ln 2. So the 3's would cancel. Let me just show you. The 3's would cancel. And the ln 2's would cancel. And you get this answer. So this answer here is actually, believe it or not, the same answer as this one right here. All right. Or not, sorry, not that one. My bad. This one. It's the same as this guy. Log base 2 of 3 minus 1 over 3 is the same thing. So you do have options when you do these. Taking the log base 2 made it a little easier because we didn't have to do the distributing. All right. So quickly looking at this one here, we had to bring down the exponent, distribute, get the x by itself, and then divide. Whereas with the way we did it previously, when we took log base 2 on both sides, I'll just copy it so that we can compare side by side. So comparing side by side the procedure, here, when you took log base 2, you did not have to distribute. You didn't end up here. Can you see the differences between these two techniques and why this may be a preferable technique, but that you totally could do this technique if you would rather have the same technique for every problem? It's the same thing with that very first problem we did. If I scroll up a bit, we could have redone this one by taking ln on both sides. If I kind of do just a quick scribbly scribble to show you that, if you take ln of both sides, and like I said, this is just a quick scribbly scribble. You don't even necessarily need to write this down. I'm just showing you that you could have done this differently. You take down that exponent, so you have 3x minus 1 ln 8 is equal to x ln 32. Distribute the ln 8, 3x ln 8 minus ln 8 equals x ln 32. Move all the x's to one side. Anything with no x goes to the other. The ln 8 moves over. You factor out the x. Like I said, you don't need to write this down necessarily. This is just, I'm just demonstrating for you that you could do it this way. And believe it or not, these are the same answer. So if I type in my calculator right now, ln 8 divided by 3 ln 8 minus ln 32, I get 0.75. But I could have done this technique. I could actually, the applying ln technique actually works in any case, all right? However, what I will tell you, because I went through your guys' homework, if you try to enter this on some of the problems where you have common bases, it won't accept this as an answer. And if you're not paying attention, it'll look like your answer is wrong, but really it's saying that your answer is not as simplified as it can be. So just kind of the reason you may not want to do the ln trick every time is because you could end up with something that actually simplifies down to a nicer number and you wouldn't know it from looking at it. But anyway, there's that. Yeah, that I 100% agree. I 100% agree. If done correctly, any technique works, and it allows for a lot of creativity. Which I love. Yes, absolutely. So hopefully I can do 2 more here. I'll go a little bit quickly. All right. We're going to do another one here. As I said before, if you don't want to think, is this Form A, Form B, or Form C, you can always just use ln. You can always use ln. It will work if you use ln. It just might be more work sometimes. In this particular case, it's actually going to be less work. So let's observe. We want to get e raised to the x plus 2 completely by itself. We want this guy all by himself. So I am going to start by subtracting 8 on both sides. That gives me -5 e raised to the x plus 2 is equal to -6. I'm going to divide both sides by -5. We get e raised to the x plus 2 is equal to 6/5. I'm going to apply ln on both sides. So I have ln of e raised to the x plus 2 is equal to ln of 6/5. And here's where some trickery happens. Ln of e to the x is equal to x, which means that ln of e to I don't care whatever is just equal to the whatever. Ln of e cancels itself out, is what I'm trying to say. Ln of e cancels itself out. All you're left with is x plus 2. But you still have ln of 6/5 over here. Subtracting 2 on both sides, you'll get that x is equal to ln of 6/5 minus 2. Just fun, excellent answer. It's important to remember those ln rules in particular. So like ln of e to the whatever is equal to whatever. It's really important to remember those rules that I put here on this first page. Like these guys right here are really important rules, really, really important rules. They don't stop being important. So with the last 4 minutes, I just want to do one more of these where it's pretty intense on the algebra. One of these really intense algebra problems. I want to make sure I go through one more in 4 minutes. Let's do it. The moral of the story with all of these, almost all of them, is once you get it so that you have, base raised to an exponent, base raised to an exponent, is it's either going to be a situation where you make them have a common base and then set exponents equal, or it's going to be a situation where ln would work. You could always use ln. So if I take the ln of both sides here, I'm not going to color code this anymore because you guys are adults and I've color coded all of it this entire time. I mean, adults still need color. Mostly I'm just lazy right now. All right, I'm bringing these exponents down. So we have x plus 6 times ln 3 equals 2x minus 1 times ln 5. So I brought the exponents down in front. A little bit of color, just a little bit. I can't stay away from the color. I'm impossible. With each of these, you are distributing the ln to both terms. So you get x ln 3, x ln 3 plus 6 ln 3 equals 2x ln 5 minus ln 5. All right, the math here is just kind of tedious. It's just a tiny bit tedious. X terms on left, non-x terms on right. So This guy needs to move over. We need to do minus 2x ln 5 because we need to move him over. And this guy needs to move over because he doesn't have an x in it, so he needs to move to the other side. You end up with x ln 3 minus 2x ln 5 equals negative ln 5 minus 6 ln 3. On the left side, you're factoring out an x. Then you're dividing both sides by this leftover stuff, the ln 3 minus 2 ln 5. So your final answer is x equals negative ln 5 minus 6 ln 3 divided by ln 3 minus 2 ln 5. Right? You're going to have at least one, maybe 2 or 3 of these problems where you need to do this algebra. So it's really important that you get comfortable with this algebra. Like I said, this is a lot like those inverse problems we did where you very similarly, like if you were trying to find the inverse of y equals 5x minus 7 over 2 minus 3x, you know, these problems where you had to find f inverse. It's the same type of algebra that we did for these guys that you end up doing over here. So that is all I have for today. You have enough information now to do the homework, the entire part 1. Like I said, I'm about to just right now start working on, finishing up the worksheet for tomorrow. So hopefully I'll have that sent out not too late, hopefully in the next hour and a half. Fingers crossed. If you have questions, I'll stick around and answer them. Otherwise, I appreciate you guys being here, interacting, being fun. You're all fantastic. Happy Tuesday. And I'll stop the recording.